So we're in chapter 6 talking about exponential logarithmic functions, and we're building up to that by this next section, 6.2, is going to be talking about one-to-one functions and then inverse functions. So we have 4 objectives. The first one is going to be to determine whether a function is one-to-one. Then determine the inverse of a function. Defined by a map or a set of ordered pairs. Then the third is going to be to obtain the graph of the inverse function. From the graph of the function. And last is going to be to find the inverse of a function defined by an equation. Okay, so objective 1, determine whether a function is one-to-one. So in section 3.1, if you think back, we talked about 4 different ways to represent a function. We had maps, where we showed the set of inputs or domain and the set of outputs or the range with arrows showing the correspondence. So that was with a map. Then we also talked about with a set of ordered pairs. Then we talked about you could have a graph or an equation. So those are 4 different ways of representing a function. So we're going to talk about each one of them in terms of the one-to-one function. So first we're going to use this, my favorite example of the pricing function. And remember we talked about that if coffee has one price, hot dogs can have the same price, and soda and chips, and this is a function as long as every item has a price and every item has only one price. We fall apart if coffee has 2 prices, because now we don't know how much to charge for the coffee. So this is not a function. And it's okay that soda and chips both are 99 cents. So that's, remember, for a function, we have every item has a price and every item has only one price. But a one-to-one function requires that each price corresponds to only one item. So another way of saying this is, from the receipt, I can tell what you bought. If the function is one-to-one. So if we have a function where coffee is one price, hot dog is a price, so each item has its own price, then this is a function and it is one-to-one. So make sure you're very clear in your mind of how do I know it's a function and how do I know it's one-to-one. So function is one-to-one by definition if any 2 different inputs in the domain, so if we have the domain here and we have some x sub 1 and some x sub 2, and over here we have the range, and you have 2 different outputs, f of x sub 1 and f of x sub 2, what it says is if x1 and x2 are different, then x1, f of x1 and f of x2 have to be different in order to be a one-to-one function. So we've looked at how to tell if a function is one-to-one using a map. How will we tell if we're given a set of ordered pairs? Well, I really like turning the set of ordered pairs into a map. You don't have to do it this way, but I like this way. So I have 2, -3, 4, and 1, and I have 6, 9, and 10 for the range. So 2 maps to 6, Negative 3 maps to 6, and that's fine for a function. 4 maps to 9 and 1 maps to 10. So this is a function, but it's not one-to-one, because it would be like having 6 over here and having two different things map here. It came from two different inputs, so that's not one-to-one. So now let's look at how we tell if a function presented as a graph is one-to-one. That's our third way: maps, ordered pairs, graphs, and equations. So we use the horizontal line test to decide if a function is one-to-one. So if every horizontal line intersects the graph of the function f in at most one point, then f is one-to-one. So remember, we talked about that this is not even the graph of a function because it doesn't pass the vertical line test. So here's a graph that is a function, but it's not one-to-one because it doesn't pass the horizontal line test. I can draw a horizontal line that runs into the function at lots of points. So if I draw a function like this, now this is a function and it is one-to-one. So we can see from the graph. So remember that there's always two ways of saying these tests. If no horizontal line intersects the graph at more than one point, then f is one-to-one. Okay, so if the function is presented as an equation, we're not going to go into that in this class. It's kind of a higher level skill, although do notice that this is a parabola, and for any parabola we can see that it's not one-to-one just by looking at the graph, right? I mean, that's obviously not one-to-one. But there is something you can do called restrict the domain, and you can say, let's just look at the domain from 2 on up, say, and oh, that piece is one-to-one. So that is something that's done sometimes. Restrict the domain in order to make a function that's not one-to-one into one that is. So in class, we'll talk about whether or not you think a function that is always increasing or always decreasing will be one-to-one. So I'm going to skip over that part because I want to talk about it in person. So the next thing I want to talk about, though, is why do you care if a function is one-to-one? And it's because of this really important result. If a function is one-to-one, it has an inverse. And this is probably really important since it's in a giant font and red with a box around it. So if we can determine that a function is one-to-one, then it's guaranteed to have an inverse. So mostly what's going to happen in your work is you're going to be given a function and told that it's one-to-one because we don't quite have the skills to test equations for one-to-oneness. So let's talk about doing and undoing. In order to undo the effect of a function, we needed a function that has the opposite effect that I like to think of as an undoing function. So you have a doing function and an undoing function. And you already know a lot of these. If the function's x squared, then the undoing function is the square root of x. If the function is the cube root of x, then the undoing function is x cubed. Okay, so here's a definition we need. Suppose a function is one-to-one. So we're given that it's one-to-one, or we have a graph we can look at. Then corresponding to each x in the domain of f, there is exactly one y in the range, because it's a function. And corresponding to each y in the range, there's exactly one x in the domain, because f is one-to-one. So the correspondence from the range of f back to the domain is called the inverse. Function of f. And we use this symbolic notation f with a superscript of -1. So this is not like when you had y to the -2, you'd say that's 1 over y squared. It's not that kind of negative exponent. It's not an exponent at all. It's just a notation that says the inverse function of f. So it's the undoing function. Okay, so in each of our different ways of looking at functions, there's another way of thinking about inverses. So here we have going from the domain of the function, which is the states, Indiana, Washington, South Dakota, North Carolina, and Tennessee, mapping to the range 6.2, 6.1, 0.8, 8.3, and 5.8. So the blue arrows, that direction is the function f, and it is a function because each item in the domain goes to one and only one item in the range. Well, then we have the inverse function, and we could represent that by different colored arrows going back the other direction. Well, now you can see for the green function, the domain is the 6.2, 6.1, 0.8, 8.3, and 5.8. And the range is the states, Indiana, Washington, South Dakota, North Carolina, and Tennessee. So the inverse function goes back the other direction. And this is a function, and it is one-to-one because each item in the range came from only one item in the domain. So we could do this with our list too, that we could say, okay, so this is a function, but it's not one-to-one. So in order to be one-to-one, we have to make sure that every price has only one item that it's associated with. So this is a function and is one-to-one. Okay, so if we have ordered pairs and we represent an ordered pair as x comma y in parentheses, then the inverse function is the set of ordered pairs y comma x, because the domain and range are reversing positions or reversing jobs. So here's a one-to-one function. Let's write it as a map because I think it's easier to see it that way. So it has domain -5, 3, 0, 2, and 7, and range 1, 3, 0, -4, -8. So you can write the domain as the set that contains -5, 3, 0, 2, and 7, and the range 1, 3, 0, -4, and -8. Well, then the inverse function has the domain 1, 3, 0, -4, -8, and the range -5, 3, 0, 2, 7. So if this is the function f, then f inverse equals 1, -5, 3, 3, 0, 0, -4, 2, and -8, 7. So you can see that in each ordered pair, the x and the y traded places. The domain and the range are changing jobs. So here's just a little visual of what's going on as you go from the domain of f, and function f takes you over to the range of f. But then if you're doing the inverse function, you're starting in what was the range of f, but because you're starting there, that's your new domain for your f inverse function, and you land in the range of f inverse. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So be super careful that the f with the superscript -1 is a symbol for the inverse function of f, and it's nothing like the exponent. So it's not an exponent, it's just a symbol. So it does not mean the reciprocal of f. If you did want to mean the reciprocal of f, you'd have to write it like this. You'd have to say f of x, that whole thing to the power of -1, and then that would equal 1 over f of x. So if you write the -1 power in here, this is the inverse. If you write the negative power out here, this is the reciprocal. So make sure you're clear on the difference between those.